Hello everyone, I presented my work Self-Perturbation. We investigated the intrinsic generality of adversarial face examples, and proposed to generate pseudo-adversarial faces by perturbing real faces with 3 heuristically designed noise patterns. We are the first to train an adversarial face detector using only real faces and their self-perturbations, agnostic to victim facial recognition systems, and agnostic to unseen attacks. Adversarial attacks aim to disturb the functionality of a target system by adding specific noise to the input samples, bringing potential threats to security and robustness when applied to facial recognition systems. Some research attempts to defend against adversarial attacks by adversarial example detection techniques which filter out adversarial samples before feeding them into protected systems. In IJCAI2023, LID is proposed for evaluating the proximity of an input to the manifold of normal examples. In IJCAI2023, SID incorporated with wavelet transforms to modify the decision boundary. And in CVPR 2021, Libra used the Bayes principle to endow a pre-trained DNN with the ability to defend against heterogeneous adversarial attacks. While all of these methods focus on utilizing features subtracted by the facial recognition backbone network and show effective performance in detecting adversarial examples, they require modifying or visiting the protected system, and tend to overfit to known attacks, and do not generalize well to unseen advanced attacks, especially generative adversarial network-based methods. We investigate the intrinsic generality of adversarial attacks. A detector for a specific gradient-based attack is able to generalize to other attacks except those based on generative adversarial networks. We calculate the Fréchet inception distance of various attacks, and it shows attack noises are to some extent similar to each other. We also discovered that generative adversarial networks made adversarial faces have manipulated clues like abnormal color aberrations in high-frequency regions. Based on the above assumptions, we proposed 3 kinds of real face self-perturbation synthesized with pseudo-noise patterns, and a max pooling-based classifier focusing on capturing abnormal local color aberration. Unlike previous methods, this data augmentation-like method is proposed from a novel and more intrinsic perspective by investigating the generality of adversarial noise patterns to detect all recent adversarial faces from unseen attacks, protecting facial recognition systems without access to them. This new framework simultaneously ensures detection performance on unseen adversarial attacks and portability in use, without any access to protected systems. Regarding adversarial faces as out-of-distribution data from a shifted data manifold, we incorporate a regularization term to narrow the model's decision boundary of real face class during training, and naturally introduce a novel cascaded system for adversarial face detection, which consists of training data self-perturbations, decision boundary regularization, and max pooling-based binary classifier. The intrinsic similarities of adversarial attacks denote that once we master all the similarities we master the attacks, even for unseen attacks. This leads to non-trivial designs for our self-perturbation. The noise value of neighbor points in self-perturbation may be the same or different. From this perspective, we introduce pointwise and blockwise noise patterns for gradient-based attacks. As presented in Algorithm 1, we perturb each point in the pointwise pattern and each block in the blockwise pattern in a stochastic direction, where blocks are random neighborhoods of a set of scattered points. The generated perturbation image is constrained in the L-infinity norm and clipped according to equation 2. And self-perturbed face is calculated as equation 3. Spectrums of real and fake images distribute differently in high frequency, such as eyes, nose, and mouth. This distribution difference should become more intense, because generative adversarial network-made adversarial faces aim to change the classification results of facial recognition systems, meanwhile maintain perceptual invariance. This leads to color aberration and boundary abnormality in high-frequency regions on account that facial recognition systems pay the most attention to these regions. Focusing on producing natural and imperceptible attack noise, these abnormal color aberrations should have gradient or blurred boundaries. In such a perspective, we use gradient color patches to act as self-perturbation. As presented in Algorithm 2, we first obtain the gradient image of a real image using Sobel operator and a convex hull of the high-frequency area according to facial landmarks. The pixels in the convex hull are selected as high-frequency pixels if their values surpass a threshold. Then we generate a few gradient color patches through a series of affine transformations. Finally, the pseudo-adversarial faces are generated by adding gradient color patches to a random set of high-frequency pixels. After crafting a part of real faces to self-perturbed faces as negative samples, we label other real faces as positive samples and train a well-designed backbone network, such as SeptionNet, in a binary classification manner. In view of abnormal speckles in generative adversarial network-based adversarial faces are always tiny and are not easy to be observed, we proposed max pooling classifier to capture abnormal local color aberrations. It produces classification scores and predicts whether input images are real or adversarial. A typical backbone network includes a feature extractor composed of several convolutional blocks, and a classifier comprising an average pooling layer, an activation layer, and a fully connected layer. To detect adversarial faces with abnormal local color aberrations, a simple derivation is to divide an image into several rectangle areas, and if abnormal color aberration occurs in any of the rectangles, we classify this image as an adversarial face. Input an image to the feature extractor, and it produces a feature map composed of n-squared features, and each feature is corresponding to a rectangle area, the receptive field. Features are sent to the activation function and fully connected layer respectively and produce n-squared logits. We take the max pooling of these logits as the final logit and obtain a prediction score by softmax operation. Although we are trying to make self-perturbed faces as general as possible, the trained network still overfits to in-distribution data and might fail to classify faces far away from the distribution of negative samples. Regarding adversarial faces as out-of-distribution data, we incorporate a regularization term into our work to enhance detection performance. Assuming the feature representation of real faces forms a multivariate Gaussian distribution, we sample virtual outliers from the epsilon likelihood region of the estimated class conditional distribution. The uncertainty loss regularizes the model to produce a low score for in-distribution data and a high score for the synthesized outliers, and narrows the decision boundary of real face class to boost the performance, where dr represents distribution of real face, f is a linear transformation function, and phi is a nonlinear MLP function. The learning process shapes the uncertainty surface, which predicts a high probability for in-distribution data and a low probability for virtual outliers. The training objective combines the real adversarial classification loss and the regularization term. To validate the detection performance of our approach on adversarial faces generated by various adversarial attack methods, we conduct extensive empirical studies on LFW and CelebAHQ datasets. We employ 8 recent gradient-based adversarial attack methods and 2 GAN-based attack methods. Previous adversarial example detection methods focus on specific tasks or gradient-based attacks, and hence can hardly be effectively extended to GAN-based ADV faces, while face forgery detection methods are used to detect GAN-made fake faces. On the other hand, some out-of-distribution detection methods only rely on output features and logits of the backbone network and keep agnosticism to unknown attacks, closing to our setting. On account of this, we compare our method to various methods in 3 problem settings. All baselines listed in Table 1 include methods of adversarial example detection, out-of-distribution detection, and face forgery detection. It is worth noting that only our method does not require either precomputed adversarial faces or access to a facial recognition system. As shown in Table 3, trained on the known attack, previous adversarial example detection methods are difficult to detect unknown attacks. In contrast, our method reaches a high level of detecting gradient-based adversarial faces and almost approaches saturation performance on the LFW dataset. We train our model with only real faces and self-perturbed faces from CelebAHQ and test both our approaches and baseline models on GAN-based adversarial faces. As shown in Table 4, the performance of our method exceeds which of other algorithms and models. This result verifies our assumption that GAN-made adversarial faces have manipulated clues like an abnormal color aberration in high-frequency regions. The 2D TSNE visualization shows self-perturbation is very close to attack noise and far from zero vector, the real faces. By separating real faces from self-perturbed faces, the trained network is able to distinguish between real and adversarial indirectly. That concludes our presentation. For more detailed information, please refer to the original paper. Thank you again for your attention.